Welcome to What Did the Code Say? Subscribe to the channel and hit the bell.
Look, if you're a beginner coder, you might look at mathematical functions and just see boring textbook formulas, right? But you've got to start seeing them for what they really are. They're the literal algorithms, the absolute source code that governs reality. Every single time an object flies through the air, or a server farm scales up, or a radioactive isotope decays, there is an invisible script running in the background. And in this explainer, we are going to crack that script wide open. So let's dive into it.
Level 1, the Parabola Protocol. So we start at the absolute base layer of our physical universe. This is where quadratic functions live. They dictate gravity, motion, optimization, you name it. And they operate as parabolas, those elegant U-shaped curves. Now, there are basically two primary frameworks for writing these quadratic algorithms. You've got your standard form, which is ax squared plus bx plus c. And then you got vertex form. And what's really killer about vertex form is the massive advantage it gives you. It is perfectly optimized so you can instantly read the h and k coordinates. That's the exact location of your vertex. Done, without doing any extra processing whatsoever.
But hey, what if your code is locked in standard form and you can't easily refactor it? Well, don't panic. You can just execute this specific formula to find the exact x-coordinate of your vertex. It's x equals negative b divided by 2a. Just run that little snippet, plug the output back into your main function, and boom, you have pinpointed your exact peak or valley.
Now, the absolutely crucial point here is knowing how the parabola executes its trajectory. And that all comes down to the leading coefficient, which we call a. If a is positive, meaning greater than 0, the parabola opens up. Think of it like a cup waiting to catch incoming data. But if a is negative, less than 0, the whole system reflects vertically, and the parabola opens down. Literally one variable controls the entire physical direction of your model. It's pretty wild.
Level 2, decoding polynomial logic. So now we're stepping up the complexity, going from a single curve to multi-layered sequential code. To really understand a polynomial, you have to find its master variable. We call this the degree. The degree is literally just the largest exponent in the entire expression. Honestly, it doesn't even matter what other numbers are scattered throughout the rest of the code. This one highest power dictates the ultimate long-term behavior of the function as it scales all the way out toward infinity.
Check out this logic table. It's basically a cheat code. You can predict exactly how a polynomial will behave at its extreme endpoints just by checking two simple things. Number 1, is the degree even or odd? And number 2, is the leading coefficient positive or negative? If you've got an even degree and a positive coefficient, both the left and right ends rise. If it's even and negative, well, they both fall. But if that degree is odd, the ends are going to go in completely opposite directions. It's a perfect predictive matrix for your graphs and behavior.
But listen, here is a crucial runtime limit that every coder needs to know. A polynomial's graph cannot just change direction an infinite number of times. There are rules. The maximum number of turning points, where the graph switches from increasing to decreasing, is always exactly one less than its highest degree. So if you have a degree of 4, your system can only turn a maximum of 3 times, period. Hard limit.
Let's crank it up. Level 3, the exponential engine. This right here is where things scale aggressively, mostly because your variable is actually up in the exponent. The entire behavior of this engine relies on its base number. If your base is greater than 1, you trigger exponential growth. We're talking about things like a 3% annual interest rate compounding on itself, or bacteria just rapidly multiplying in a server room petri dish. But if your base is less than 1, you trigger exponential decay. Think of a drug metabolizing and filtering out of a human body at a steady rate of, say, 11% per hour.
And honestly, this brilliantly illustrates the sheer, raw power of exponential growth. Just take the global population, for example. Back in 2010, the UN tracked it at 6.79 billion people with a 1.1% yearly increase. If you plug that exact data into a standard exponential growth model, so that's 6.79 times 1.011 to the power of t, and you run that script forward 40 years, it projects a staggering global population of 10.5 billion by 2050. That is exactly what happens when data continuously multiplies upon itself.
Now let's flip it and look at the reverse script decay. Carbon dating actually uses exponential decay via half-lives to essentially hack time itself. Say a researcher finds an ancient bone that has decayed from 200 grams of radioactive carbon-14 down to just 40 grams. Well, we can just run a continuous decay model on that to find out exactly how long that process has been running. The output?
That bone is 13,351 years old, just from reading the math.
But that actually brings up the ultimate hacker question. In that carbon dating equation, the variable we desperately needed to solve for, the time, was completely trapped up in the exponent. So how on earth do you reverse engineer a piece of code when the variable you need to isolate is stuck up in the sky like that?
Simple. You use the ultimate mathematical decryption tool, the logarithm. Logarithms are the literal inverse of exponential functions. They are specifically designed by the math gods to undo exponential functions and pull that trapped variable right down to the baseline so you can actually read it. Saying log base a of b equals c is exactly mathematically the same as saying a to the power of c equals b. It perfectly isolates the exponent.
Which brings us to level 4, debugging mathematical errors. We are going to use these logs to hack some seriously complex equations. So, here is your rapid-fire cheat sheet for log syntax. First, the product rule. The log of a product splits into the sum of the logs. Easy. The quotient rule. The log of division splits into subtraction. But listen, the most important command in your entire arsenal is the power rule. The log of x to the power of n equals n times the log of x. This specific command is exactly what allows you to grab an exponent, rip it down from the top line, and multiply it on the main line. It's a real game changer.
So whenever you hit a tricky exponential equation, here is your exact 4-step execution algorithm. Step 1. Isolate the exponential part of the equation. Just clean up all the surrounding numbers first. Step 2. Take the log of both sides. Usually you'll want to use natural log or base 10. Step 3. Execute that power rule we just talked about to bring the trapped exponent down to the baseline. And step 4, isolate and solve for your variable. I promise you it works every single time.
But listen to me very carefully on this one. You have to watch out for extraneous solutions. Sometimes you'll run this algorithm, the math will spit out an x value, and if you plug it back into the original code, you'll trigger a fatal error. Why? Because the domain of a logarithm strictly, absolutely requires positive numbers. You cannot take the log of a negative number, and you literally cannot take the log of 0. If your solution forces that to happen, it is a phantom bug, and you have to throw that data out immediately.
And while we're on the subject of debugging, let me highlight a classic rookie mistake that will completely break your logic. The log of a sum does not equal the sum of the logs. Let me repeat that. Log, parentheses, x plus y, close parentheses, is not log x plus log y. There is absolutely no mathematical rule that lets you split up the log of a sum. If you try to force it, your whole system crashes. Don't do it.
From parabolic protocols tracking motion to exponential engines scaling populations and log decryptors solving the unsolvable, math isn't just numbers, it is the raw algorithm of reality.
If you want to understand what the code says before it explodes, hit subscribe. Don't forget to like. This tells YouTube that technical content is still alive. Share this with a beginner coder who needs help. And you, what did the code say in your project today?